Hi, everyone. Thank you for attending today's webinar, Understanding Battery Chemistry. What is the best battery for my solar energy system? I'm Kelly Pickerel, editor with Solar Power World. And before we get started, there are a few things you should know. This webinar will be sent to all registrants so you can view it again. Slides are available to view at any time in the resource widget at the bottom of your screen. Please submit any questions related to today's webinar in the Q&A widget. We will try to answer these during the webcast, and if we do not get to your question, our presenters may reach out to you after the broadcast. And finally, if you are watching this on demand, you can still use all of these features. So let's get started with today's webinar, Understanding Battery Chemistry. What is the best battery for my solar energy system? Today's speakers are Stacy Delzies, who is Senior Applications Engineer for Trojan Battery Company, and Michael Sherman, who is Inside Sales Representative for Morningstar Corporation. Today, we'll discuss the differences between battery types and the importance of maintenance on energy storage systems. And now, I'll turn things over to the team.
Thanks, Kelly. Good morning, everybody. I'm Stacy Delzies from Trojan Battery. We are so glad all of you are taking time to join us today. We're going to talk about different battery options that are available and how to decide which one is best for your solar system. Before we get into the topic, I wanted to make sure that everyone is aware that C&D Technologies and Trojan Battery are now one company. Back in December of 2018, C&D acquired Trojan. We're both battery companies, been in business for nearly 100 years, both of us, and but the applications we serve and the products we make are very different. So as we move forward, it's exciting to see where things may go with us as a combined company. So now we're going to jump into our topic. There are a lot of choices when it comes to battery solutions these days. We've got flooded lead acid, gel, AGM, lithium ion. It's really hard to decide what battery is best for you. But choosing the right battery type is important to make sure you're satisfied with your system. Knowing what is expected from the batteries is key. And this means that we need to understand factors such as battery maintenance requirements, service life, the investment, how much money do we want to put into it, and even operating temperatures. We're going to cover various battery types, and hopefully you will understand the different details about those battery types, so it will help you make a choice in your system. And then we also have a costing model that we're going to talk about that focuses on total cost of ownership rather than just the initial purchase price. Moving into the factors that we need to consider when we're looking at battery systems, we need to evaluate the daily energy consumption, the maintenance needs. This includes watering and charging. We want to look at cycle life expectations, how long it takes to recharge the batteries, the recyclability of the product, the cost, and then, of course, safety. Depending on those factors, there may be a good, better, or best choice. There's not always a clear-cut winner, but we can, kind of assign good, better, or best. So we're going to start with flooded lead acid. This is certainly the most tried and true technology that we're going to discuss today. Flooded lead acid batteries have been used since the 1800s. So we've got a picture here of a cell, what it looks like, and basically what we have is alternating positive and negative plates with separator in between them. The grid alloy that's used is a lead antimony alloy, and then we put active material on the grids. So on the negative, the active material is lead. On the positive plate, the active material is lead dioxide. And the sulfuric the electrolyte that is used is a dilute sulfuric acid. And then looking at the container that we put the cells into, it's typically made of a polypropylene or polyethylene material. This material is not only chemical resistant and very durable, but it's also recyclable. And you know you have a flooded lead acid battery when you see vent caps on the top of the battery that can be easily removed to allow you to add distilled water. So looking at the characteristics of flooded lead acid batteries, you're going to have to add water to them every 4 weeks. I mean, it depends on how the batteries are being used and how they're being recharged, but you are going to have to add water to them. There are single-point watering systems available these days to make that chore faster and more accurate and just easier in general, but there's an additional cost associated with those systems. And you're also going to need to clean the terminals periodically because corrosion does build up. As far as cycle life goes, you can be anywhere in the 1,200 to 3,600 cycles at 50% depth of discharge, just depending on which battery model you're looking at. Charge time, if the batteries are fully discharged, you're looking at around 8.5 to 9 hours to get them recharged. Lead acid batteries are very recyclable, and there is value in the spent battery or the core at the end of life. The initial cost is low. There are some safety concerns, though. We have to be concerned about spilling electrolyte, and then also flooded batteries generate hydrogen gas when they are charging, so we may need to look at ventilation requirements to make sure the hydrogen gas doesn't become a safety issue. And as far as initial capacity goes, the batteries don't provide 100% of their capacity when they're new. It takes 50 to 100 cycles to work up to that peak performance. So moving on to AGM batteries, these batteries have been around since the 1970s. They are sealed. They're considered non-spillable. There's no free electrolyte. All of the electrolyte is absorbed in this white separator material that you can see over here in the picture we have. Because the batteries are sealed and non-spillable, it means you can mount them on their sides or on their end if needed. That can be handy sometimes. One of the main differences between AGM and flooded batteries is that the grid alloy we use with AGM batteries is a lead calcium alloy rather than a lead antimony like we use with flooded batteries. The active material on the grids is the same. The negative plate is lead, the positive plate is lead dioxide. And again, we're connecting positive and negative plates together. They're separated with the white absorbed glass mat. It's a fiberglass type material. That's the separator material. And the electrolyte is still sulfuric acid. The container is also polypropylene, polyethylene, just like flooded batteries. You know you have an AGM battery because there are no easily accessible ports to add water. There's no tops that easily remove to add water to the batteries. So as far as characteristics of AGM batteries, they are maintenance-free in terms of watering, but you're going to have to periodically clean the terminals. Cycle life is between 1,000 and 1,700 cycles at 50% depth of discharge, just depending on the battery model. Recharge time is going to be around 9 hours if they're fully discharged. They are very recyclable, and there's value in the spent battery at the end of life, value in the core. The initial cost is a little higher than flooded batteries. Very few safety concerns because we don't have to worry about the acid spilling or the gassing that happens with flooded batteries. And they do have peak performance within the first 10 cycles. So now we're going to move into gel batteries. Gel batteries are very similar to AGM batteries. They've actually been around since the 1950s. The difference between AGM and gel, the alloy grids are the same, the active material is the same. What becomes different is that a silica is added to the liquid sulfuric acid in order to cause it to gel up and make it non-spillable. So again, these are very similar to AGM. You can mount them on their sides or on their ends if needed. The containers are still polypropylene, polyethylene, and there are no filling ports or obvious vent caps on the top of the battery. For maintenance requirements for gel batteries, you're not going to have to water them. You will periodically need to clean the terminals. The cycle life is a little lower than AGM's, around 1,000 cycles at 50% depth of discharge. Takes about 9 hours to recharge them if they're fully discharged. They are very recyclable, still have that core value at the end of life. The price is going to be a little higher than AGM or flooded. Very few safety concerns, and they do provide 100% of their capacity very quickly. Now, moving into lithium-ion batteries. These were developed in the 1980s, really commercialized in the 1990s, and there are several different lithium-ion chemistries out there. As far as the negative electrode goes, all of the different chemistries use a carbon material for the negative electrode, but then the positive electrode varies depending on what the chemistry is. It could be a lithium cobalt oxide, it could be lithium iron phosphate. It just varies depending on what the chemistry is. There's a separator material between the positive and negative electrodes, and then there's an electrolyte. In this case, the electrolyte is a lithium salt in an organic solvent. And as far as the package goes, they can be cylindrical, they can be prismatic, they can be pouch cells. It really does vary, lots of options there. And there are safety concerns with lithium ion because the battery management system is required to make sure that the individual cells are being monitored and being protected. So definitely some safety concerns that dictate the use of a battery management system. As far as some of the different chemistries, the oxide-based chemistries, so it may be a lithium cobalt oxide, lithium manganese oxide, there's several different ones. They tend to have very high energetic thermal runaway. So what happens if one cell in the pack fails and has an issue, it quickly propagates to its neighbors. And before you know it, the entire pack can fail. And this can get pretty dramatic sometimes. I mean, you guys have probably seen videos or pictures or something of this type of failure. The phosphate-based chemistries are actually safer. They don't have that energetic thermal runaway, very little oxygen evolution. So that's probably the main reason that Trojan chose lithium iron phosphate to go with, as our chemistry of choice. Now, as far as characteristics of lithium-ion batteries, there is no maintenance. Cycle life at 70% depth of discharge is about 6,000 cycles. Charge time, varies like with any battery charging, but because it depends on the charger that you have available. But even if they are 100% discharged, they can be recharged in 5 or 6 hours. Definitely can be recycled. However, there is a cost associated with that recycling. So at the end of life, there is a fee in order to get the batteries recycled. The initial cost is high. There are some safety concerns that we talked about. It can be fires, explosions. And because of that, it's really important that the quality and the design of of the cell and of the battery management system be considered. And they will provide 100% of their capacity at cycle 1. Now on this slide, what we've attempted to do is give each battery technology a score between 1 and 4, and looking at different attributes, mounting and environmental restrictions, maintenance, power, cycle life, operating temperature range, charge time, recyclability, safety, and initial cost. So when you look at it, it's not like there's one battery type that got all 4s or one battery type that got all 1s. So you really have to kind of weigh those different attributes and decide which is most important to you, and then look at the different options and what each technology brings to the table. So we're going to do a total cost of ownership. Now this is it's a pretty simple example. We're using our battery sizing calculator in order to input the data, and then it's going to give us some battery model suggestions, and then we'll look at the different costs associated with those suggestions. So if you're not familiar with our battery sizing calculator, you can find it online at batterysizingcalculator.com. You can also get to it from the Trojan battery website. But the first step, you basically have to put in the key design parameters for your system. So in this case, we chose a 48-volt off-grid system. We're going to allow a design depth of discharge of 50%. Any battery type is being considered, and we're just allowing for 1 day of autonomy in this example, because we would assume we have a generator backup. So that's the first step. In the second step, we look at the daily load requirements. And you can add as many line items here as needed, but in this case, we're just doing a very simple. We've got lights, a television, and a refrigerator. We tell it how many of each, how many hours the device runs per day, and how many watts the device requires when it's running. And then the system does all the math, crunches the numbers, figures out the watt hours here, and then looks at the 50% depth of discharge that we put in step 1, and knows it's a 48-volt system. And the system accounts for some inefficiencies in the wiring, and to make sure that we're not going to overstate or understate the load. And the outcome here is that we need a 205 amp hour battery bank. So that's the end result, is we need a 205 amp hour battery bank. That means we will, at the end of the first day, because we have just 1 day of autonomy, the battery bank would be 50% discharged. So the next part, the output of battery sizing calculator, is battery choices. So in this case, we have basically something from every one of our battery families. We have a solar AGM, a solar signature, a gel, a lithium, a solar premium, and a solar industrial. The system tells you how many batteries you need, how many strings in parallel, the calculated depth of discharge, based on the capacity of the battery. And then finally, it gives you a calculated cycle life that's based on, the depth of discharge. So how many cycles you can expect to get from the batteries. Now, one thing to keep in mind, anytime you see a cycle life number, especially, with batteries that require maintenance, that assumes good maintenance, right? You have to recharge the batteries properly, and you have to water the batteries properly. So that's what these cycle life numbers are based on. And then we've got a spreadsheet model here. There's a lot of numbers on it. Hopefully you guys can see the numbers. But a lot of this is the same data that came from the battery sizing calculator. In our model, we are assuming a design life of 20 years. And, we've got the different models here: solar signature, flooded premium, flooded industrial, then gel, AGM, and lithium ion. We've got the battery weights included here because we're going to use that for recycling numbers down at the bottom. We've got the battery capacity, how many batteries we need per, of each battery type. And then there is a price. It's an offer per unit. So this is a reasonable sales price. Our sales team provided us these numbers, and this should be a number, pretty close to what you could go obtain one of these batteries for. And then, the spreadsheet's just doing the math. You need 4 batteries of these, so it's doing the arithmetic. And then we end up with an expected battery life, how many years the battery is going to last. And considering that we want the system to be designed for 20 years, we're using that battery life to figure out how many times the batteries need to be replaced over the 20-year period. We attempted to include a maintenance cost because the flooded batteries require maintenance in the form of watering. Now, we put $20 in there, $20 per time, and you're going to water them 4 times per year. These numbers, of course, can vary. As a homeowner, you're doing the maintenance yourself. It really doesn't cost you much more than, a gallon of distilled water. But in some cases, you may have someone coming out and helping with the maintenance, taking care of that. So we just wanted to include something because there is a cost associated with maintenance, even though we can't, 100% define it correctly. And then at the bottom here, we're figuring out the maintenance cost over the system's life. We put a change-out cost in there because, again, there's some cost associated with changing out the batteries each time they have to be changed out. And so there's value in batteries that will last longer. You won't have to change them out as frequently. And then there is a recycling or disposal line. In the case of the lead-acid batteries, this value is negative. It's not a cost, it's a credit. It's based on the price of lead and the weight of the battery and how many batteries are used. And then in the case of the lithium ion, there is a cost associated with recycling those batteries. Again, we're using today's value and the weight of the battery. And then finally, you add up all the numbers and you end up with a total cost of ownership in terms of dollars per kilowatt hour. So the lowest cost are the green numbers, and then we've got, the next range are the yellow values, and then the red is the most expensive. So, this is just our model where we tried to do this, take all the different features and requirements into account, and it's interesting to see, the different, the way the total cost of ownership ended up. So, that pretty much finishes my part for right now. So I'm going to hand it over to Michael from Morningstar, and he can continue on for us.
All right. Thank you, Stacy. And before I forget, thank you very much to Trojan and Solar Power World for having us today. We certainly appreciate the opportunity to talk about us and our products and, obviously how it can support your batteries in your solar system. So once again, my name is Michael Sherman. I'm an inside sales rep with Morningstar, and I'm going to talk a bit about Morningstar, our products. I'll give you some examples of off-grid systems, and then at the end, we'll do a sizing example with a Morningstar controller and Trojan batteries. So to start, Morningstar is a U.S. company that conducts business through our network of authorized distributors and dealers all over the world. We've been in business since 1993, and we are a leading supplier of solar charge controllers and inverters. We've had the same ownership, management, and distribution partners throughout our history. And we pride ourselves on product quality, reliability, and innovation. So to date, over 4 million Morningstar products have been supplied since our founding in 1993. We have a very diversified product line and the lowest failure rate in the industry. Now, our products are used in off-grid power systems in a lot of different markets for a lot of different applications. One application, and there's a reason why I'm bringing this one up first, is rural electrification. And I say this one because we just finished what I believe is the largest project of its kind in the world, where we supplied power for 175,000 homes in Peru. And this project, I believe, will affect as many people, as much as 3 million people across the country. So in addition to residential and rural electrification systems, Morningstar products are used in industrial applications at remote oil and gas sites, telecommunication sites, for remote monitoring, traffic control, solar lighting, and railroad. Now, to be clear, all of these applications differ from the grid-tied systems that most people are used to seeing in neighborhoods, where the homeowners are selling back power to the utility company. The off-grid power applications that use Morningstar controllers are remote sites that are not connected to the electric grid. There's no utility company involved, and all power has to be generated by a system at the remote site. Now, the obvious question is, why off-grid? The main reason why people build off-grid systems rather than connecting to the electric grid is usually predicated on cost. It costs approximately $15,000 per mile of wire to connect to the grid, and that cost can be even higher if there's difficult terrain involved, like mountains or rivers or forests. So the solar charge controller, what does it do specifically? In short, the charge controller converts the PV panel voltage to the proper output for the battery, and this maintains the battery at its highest state of charge while protecting the battery from overcharge by the solar array. Now, some controllers include low control for low voltage disconnect. That protects the battery from over discharging. And in addition, they can offer lighting control to turn lights on during the evening and off during the day. And you'll see that later on in the example that I'm going to use. Charge controllers can also provide system status indicators with meters and LEDs to display battery voltages, current, system operating temps, and other alerts. Additionally, some controllers include data logging and remote monitoring capability as well. Now, the charge controller generally represents about 10% of your total system costs. Now, a good controller will extend battery life by keeping it healthy with proper charging. And batteries can be 40% or more of your first-time cost and as much as 80% of the lifetime cost for your solar power system. Now, a poor controller, vice versa, can cause battery failure and even complete failure within the entire power system. And I'll show you where a controller fits into an off-grid system in a bit. But first, we're going to take a look at the two major types of controllers. All right, so Morningstar offers two types of solar charge controllers. We have pulse width modulation, or PWM, and maximum power point tracking, or MPPT. Now, we get a lot of questions about the differences between the two types and usually which one's better. And really, they are both very good controllers. They do utilize different technologies, so they're intended for different types of systems, but they're both very high quality. Really, the difference is mainly in the applications and where you want to use one over the other. MPPT controllers operate at the maximum power voltage, or VMP. Morningstar controllers include very fast tracking, which means that the controller will continuously operate at that VMP during bulk charging to deliver the maximum amount of power possible from that array of panels. MPPT controllers can also operate with much higher voltages and lower array currents than other controllers, which can mean fewer strings in parallel and smaller wire sizes since there's less voltage drop. Now, this can be done with either larger panels or by wiring multiple panels in series. Our MPPT controllers are buck converters, which means they can step down those higher voltages to the battery voltage. And it's a real advantage with MPPTs because it allows them to be very flexible regarding what panels are used and how they're wired. And then last but not least, because they work at the maximum power voltage, MPPTs can get more energy from the panels than a PWM, which, as you'll see on the next slide, need to operate at the battery voltage. And I usually tell customers anywhere from usually around 20%, but you can get as much as 30% more power. The second type of controller are PWM, or pulse width modulation. PWM controllers tend to be physically smaller, and they operate at battery voltage. Because they work at the battery voltage and are not buck converters like MPPTs, PWM controllers need to be used with arrays that are matched with the battery voltage, which limits what modules can be used. So for example, if you have a 12-volt battery, you need to use what are called 12-volt nominal panels. Solar panels that are nominal voltage are generally labeled as such. They'll usually say 12 volt or 24 volt, but they might also call themselves 36 cell for 12 volt or 72 cell for 24 volt. Now, in contrast, there's a lot of solar panels on the market that are what are known as 60 cell modules, and they have a VMP equal to about 30 to 36 volts, which would be equivalent to an 18-volt nominal panel. Those panels are not compatible with PWMs, and that's where an MPPT would be necessary since the voltage is too high for the battery. Now, it's easy to think that MPPT is always the better choice, but the advantages of MPPT, they do come at a cost. So PWM controllers can very often be more cost-effective with smaller systems and in warm climates where the MPPT boost from low temperatures isn't as significant. PWM controllers also work very well in locations with consistent and abundant sunshine. All right, so let's move on and see how a controller fits into an off-grid system. All right, so this diagram displays the Morningstar controller and other components of an off-grid system and how they are connected to power a direct current or DC load, which is the light in this example. So what happens is sunlight contacts the solar modules, which convert solar into DC electrical power that it delivers to a charge controller. Charge controller regulates the amperage and voltage that's delivered to the loads, and any excess power is delivered to the battery system so that the batteries maintain their state of charge with, again, not getting overcharged. During the evening, when there's no sunlight, battery power is used to run the load. Now, you'll notice that the battery is grounded at the negative battery terminal. And this is because all of our PWM and MPPT controllers have a common negative ground. So it's possible to establish a common negative ground for the entire system, the solar array, the battery, and the load. And this meets NEC code requirements for grounding. If you need an equipment ground for any metal parts on a controller enclosure, some of our controllers do include a ground terminal lug. Otherwise, you can connect an equipment ground directly to the controller enclosure. All right, on the next slide, we will take a look at a similar diagram with an AC load. All right, so this diagram with an AC load looks very similar to the previous example with the DC load, except that here we've added our SureSign inverter to the system. And the purpose of the inverter is to convert the DC power from the battery to AC power that can be used to run an AC load like the TV that's on this example. Now you may have noticed that we're connecting the inverter from the battery, not the controller's load terminals like we did for the DC load. And that's because the inverter can have a very high energy surge on startup, and the high current surge might be higher than the rated capacity for the controller versus the batteries, which can meet that high energy requirement. All right, let's move on to sizing. So as you can imagine, much like I talked about earlier, some of the most common questions that we get are about how to pick out the right controller, not just MPPT versus PWM, but also what size of controller. And to do that, to find the right controller, we really need to know all the components of the system. So what we're really doing is getting into system design and sizing. So here on this slide, you can see the usual steps involved with system design and sizing of a system. And you'll notice that picking out the controller is actually one of the last steps involved. Step number one, just like we saw earlier in the presentation when Stacy went over their load calculations, the first step is evaluating the load. Basically, you need to know what you are going to power and how much power you're going to need to do it. From there, just like Stacy again showed us earlier, you can determine what size of battery or batteries that you need. You can pick out the type that you want, whatever works best for you, so on and so on. I'm not going to go into a whole lot of detail with that since Stacy did such a nice job of covering it already. But the calculator that she showed, that's the type of thing that we use to answer that type of question. What's the best battery? How much do I need? Once we have the batteries picked out, then we can calculate how much solar power is necessary based on, the average amount of sunlight for the area. And for what it's worth, there are solar maps available online. It's kind of a neat thing. What you'll find, at least it's fascinating to me, is how much it varies across the globe by where you are, how much available sunlight happens. It's super neat. It's great. There's a lot of information out there. All you really need to do is Google solar maps, and you can find all you need. Having said that, when it comes down to it, what we are after when it comes to sunshine and how much is going to be available, we always use the average number of sun hours during the day during the least sunniest month of the year, not the whole year. So we basically are going to almost worst case scenario plan the system sizing so that there's enough solar power even in the dead of winter. Once we have the panels picked out, we can choose a controller that is appropriately sized for those panels and the battery. And then, of course, we would take into consideration any other features that are needed, like meters or low voltage disconnect, load control, data logging, and so on. For systems with AC loads, sizing an inverter would be step number 5. All right, so here is the example that we are going to use today. So what we're going to have is three 20-watt LED bulbs. We want them to run for 4 hours every night. We want to make sure that we have at least 3 days of autonomy, and what that means is that the system can run for 3 days even without any solar-powered charging. So if it's 3 days straight of rain or other bad weather, whatever the case may be, these batteries are still going to be sized appropriately to keep that light running on schedule for those 4 hours. What you're going to find is that once we get through this exercise, we are going to select the Trojan batteries here, the Solar Premium. They're the 6-volt, I believe, 229 amp hour batteries. And then we will end up with a 300-watt panel and a Morningstar ProStar MPPT. Actually, I believe I chose the 25 amp metered version. So the SKU for that is PS-MPPT-25M. Now I want to note this system is going to be in Seattle. So much like I was talking about before with the solar maps, we are going to have a pretty low amount of sunlight available, which will affect the calculations. Compare that to somewhere like Phoenix, where there's an abundant amount of sunshine and it's always warm. Let's see here. And that should be about it. Let's take a look at what it looks like on our DC load diagram. All right, so this is the same diagram as we used earlier in the presentation, except now we've got the products filled out and we've numbered the steps involved. So if we start on the right at 3 o'clock, we've got number 1, which is the load. Number 2 is at the bottom, that'd be the battery. Number 3 is the panel. Number 4 is the solar charge controller. And there is no number 5 because this is a DC load example and we don't need an inverter. So, all right, let's go through it. We found our 3 lights and the amount of energy needed to power every day for 4 hours, which ended up being 240 watt hours. Put that in the calculator, just like Stacy showed earlier, and made sure that we got enough power for 3 days of autonomy, as I mentioned before. And basically came out with a decision to use the Solar Premium batteries here. Now these are 6-volt batteries, so we got 2 of them wired in series to get to 12 volts. From there, we figured out how much solar power was going to be necessary and picked in a panel that's appropriate. Now, the panel that I chose is a little bit bigger than what we actually need. When I ran the numbers, it was closer to, I think, 250 watts that we needed to successfully power this system. But I chose a 300-watt panel for a couple of reasons. One, having the one panel keeps it from getting overly complicated with how we want to wire and that type of decision. And also, in the end, 300-watt panels are pretty common and they're pretty affordable. It's actually going to be less expensive to do it with one panel, one larger panel, than, say, 2 smaller ones. So because we are in Seattle and because it is a low light part of the world, that is where the driver was for the larger 300-watt panel. Interestingly enough, I did the same calculations in Phoenix, and I think we needed about half as much panel to make this system charge correctly. So geographics definitely play a big role in the decision-making process here and sizing appropriately. All right, and then from the panel, we chose the controller. Now, as I mentioned when I was describing the differences between the 2 controllers, because we have a larger panel that is higher voltage, we can't use a PWM in this example. We do need to use the MPPT. But having said that, MPPT is a great fit. It's going to work perfectly, and it's going to get a lot of energy harvest from this panel to charge those batteries. Now, I also selected the specific controller that I did, the ProStar MPPT, because both of our ProStar PWM and our ProStar MPPT controllers have very robust lighting control options. And in particular with this one that's shown here with the meter, you can use the scroll buttons on the face of the controller and the meter to program the lights and when you want them to turn on and turn off. Now, originally we just said 4 hours, but we didn't say when, and we didn't say if it was straight or if it was going to be broken up. So with this controller, we can very easily program to have the lights come on right at dark and stay on for 4 hours. We could program the controller to turn the lights on for 2 hours when it gets dark, and then 2 hours again before the sun comes up. Really whatever we want, whatever combination we want. And what's really interesting is that this works on solar time. So we're not going to program in, turn the lights on at 7 o'clock. We're going to say, like I said before, turn the lights on at dark for 2 hours, and then again before dawn, 2 hours. So it'll keep up with the naturally changing schedule, the weather patterns and the calendar year. So as the days grow longer or shorter, the controller will adjust naturally. All right, and that's really pretty much it with system design. For what it's worth, it's something that's very important to point out that this process, these steps, they're really the same no matter what size system you're doing, whether it's something very simple like what we just described with the lighting, all the way up to large-scale industrial projects that you might find on a cell tower or involved with an oil and gas pipeline, anything like that. They all really use the same basic premise to size and select the right products and make sure that the system will be powered correctly and last a long time. And I think that's it. I believe that is the end for me. I will kick it back. Stacy, are you up again?
I am, yeah, thank you.
All right.
Yeah,
thank you.
Yeah, thanks, Michael. That was a lot of great information. So just moving back to batteries for just a minute here to kind of summarize. Unfortunately, there's not one silver bullet, right, for all renewable energy applications. The best battery type choice, I mean, that's going to depend on, what you want from the system, the service life, the cost, all those factors that we talked about earlier. So it's good to have those options. That's one thing that's nice, to have options, because not everybody's going to want the same choice. Some customers are going to want to have the latest and greatest technology. So again, it's good to have those options, but then it's also good to realize that there's not one best option for every situation. So hopefully you understand more about the battery technologies that are out there and how many, many factors impact the system's total cost of ownership. It's really not an easy thing to answer. And then, we just want to thank you. Thank everybody who's on attendance. Thank you for taking the time to come today. Thanks to Solar World for facilitating this event. You've got Trojan's and Morningstar's contact information here, websites, emails, phone numbers, whatever. You can reach us anytime, and we are always glad to assist. So with that, I'm going to hand it back over to Kelly.
All right. Thank you, guys. We do have a few minutes here for some questions, and so please, you can submit your questions at the Q&A widget at the bottom of your screen. So our first question, can you talk a little bit more about the calculator that you guys have? Does it focus primarily on solar projects to pair with energy storage, and is it open access to everyone?
It does focus on solar. We have not expanded it to include, options like wind or hydro. It really does focus on solar at this point. And as far as open access, I mean, anyone can use the system. It's just batterysizingcalculator.com. But the battery choices that are going to come up are going to be Trojan battery choices, because we developed the tool. So, that's kind of what we're trying to do is give options for Trojan battery choices.
Perfect. Our next question, are there restrictions to where the batteries are located? Do they have to be in a dwelling?
Some of that is going to depend on the battery type. Flooded batteries produce hydrogen when they're charging, so you do have to look at ventilation requirements. You may or may not need forced air ventilation. It all comes down to the size of the room and how many batteries are charging. Now, we are not ventilation experts, but we do have a calculator that can assist with determining how much hydrogen a given battery system is going to produce, if you're concerned about that. With lithium, there's no concerns around those, type of, you just don't have to worry about it. So, but yeah, with lead acid, you do want to look at it, and we're glad to help if we can.
Specifically about lead acid batteries, how often should I water flooded batteries, and is there an easy way to water them?
Well, how often you're going to need to water them really comes down to how they're being charged. Batteries lose water in proportion to the overcharge they receive. Now, when I say overcharge, sometimes people, freak out. I don't want to overcharge my batteries. But the fact is they have to have some overcharge in order to be fully charged. So with solar systems, quite often they aren't even fully charged. They operate at a partial state of charge. So you're not going to have to water very often. With something like a golf application, where you just plug them into a AC powered charger, you're going to have to water them every 4 weeks, definitely. But as far as an easy way to water them, we do have single point watering systems. These are devices where you remove the battery's vent caps, you replace them with the single point watering caps, and the watering caps have a level. There's a little float in there. So when the electrolyte level is where it should be, no more water can be added to that battery. So there's a series of tubes that connect the different single point watering caps, and it just makes that chore of watering batteries faster, more accurate, easier. You don't get acid on your clothes, that type of thing.
Okay. Our next question, what are the cycle figures based on?
For our solar batteries, and I should have said that, that's a great question. There is an IEC test standard, it's IEC 61427, and that's what the cycle life figures on our solar products are based on. Now we have other batteries that, that we market to, motive applications, golf applications. Those are tested differently. But the IEC 61427 is an industry standard for testing batteries used in solar applications. So that's what they're based on.
Okay, great. So with Trojan's Trillium line of batteries, are there applications where lithium is not always a good replacement for lead acid?
Certainly, yeah. It's definitely not one size fits all, like we've kind of been saying today. One of the biggest things is charging during cold temperatures. I didn't dwell on that today because we're not really, talking about properly charging batteries. But the fact is, when it's below 32 degrees Fahrenheit, charging lithium-ion batteries is different. And how you manage that, it's not part of the battery management system. It is something, that's outside. So certainly if the batteries are going to be in cold conditions, you've definitely got to look at it, because it becomes not only a performance issue, it can become a safety issue if lithium batteries are charged when they're too cold.
Can you repeat the battery tool website again?
It's batterysizingcalculator.com, just all one word.
Okay. Looking through our questions. On the differences in charge controllers, I noticed that PWM is always less expensive than MPPT. Is there a quality difference between them?
Okay, good question. Absolutely not. They are both excellent controllers. We, depending on the product line for our professional series, we have a 5-year warranty for all controllers. For our essential series, we have a 2-year warranty. But the short answer is no. They are both great quality. As I mentioned in my section, it really comes down to what's the best fit for the system. And a lot of times, where is the system, what products are being used elsewhere, and then work your way towards what's the best choice for you.
Okay, this will be our last question. For mobile applications, do we ground the battery to the vehicle?
In most cases, no. I mean, that can be somewhat system dependent, but in most cases, no.
All right, perfect. Well, that is all the time that we have for questions today. If you have additional unanswered questions, please feel free to contact our presenters on your own. And this webinar will be shared with all registrants again, so you can view it at your convenience. I would like to thank Stacy and Michael for being here, and Trojan for sponsoring today's webinar. And thank you to everyone in our audience for participating. Hope you enjoyed the presentation, and we invite you to join us for more Solar Power World webinars in the future. Thanks, everyone.